we just began soda ash, and then I told you that it's always a good idea to get some feel for the kind of applications of these products. That's what makes these products so important. And we talked about glass. That's one of the biggest applications of soda ash. Actually, this was pivotal in really leading up to the important work of Leblanc and Solvay. Just to give you an idea also of innovation, so that laterally it's not directly got to do with soda ash, but it's got to do with glass, which is linked to soda ash. One of the very important glass today is float glass. Have you heard the name float glass?
No, sir.
Okay. Earlier days, a lot of the glass used to be made by blowing, glass blowers. That's what we had. But if you look at all your window panes and everything, what do you have? You have a flat glass. And in fact, today the glass is really so wonderful. There's virtually no distortion. Whereas earlier days, sometimes you can see your reflection in the glass and you see yourself all distorted. Today, I mean, things have really improved. The other thing is that the glass is flat on both sides. It's smooth on both sides. It's not as if one side is uneven and the other side is smooth. Both sides are smooth. Now, if I have to ask you, how would you make a glass which is smooth on both sides?
So we would melt the glass, and
Okay.
then as we using hydraulics, we would compress it on both sides, and while it's still hot, we would cut off the sides that would come out.
Compress it on both sides means it will be resting on something, or
Yes, sir. Like we'll have an hydraulic system where there is a flat surface
yeah,
on
what is
both
that
sides.
flat surface?
It should be a metal.
Metal. And so you're talking about a solid metal surface on which the glass is formed, right?
Yes, sir.
Now, only thing is, I mean, you'll have to also make sure that the thing doesn't stick to the metal because it might be then difficult to take out the glass from the metal. So it has to have that property. And of course, your metal has to be very, very smooth because you have seen how smooth the glass is.
Yes, sir.
I think you really need a shiny metal surface. That's possible, and in fact, there is a metallic surface which is used, but slightly different from what you might think. What happens is exactly as you said. First, you will melt the glass in a melting furnace. We are talking about the soda lime type of glass, which is also known as window glass. And this is typically the composition. And all of these, as I told you, I mean, this is all silica, and inside it, you will find the impurities of calcium oxide, sodium oxide, alumina, MgO. All of these things will be sitting in it, and that's what actually distorts the structure and lowers the melting point. So that's what you have. We said that glass will melt around maybe around 1000 degree or a bit less or a bit more, depending on the composition. Now, what this person, Sir Alastair Pilkington, I mean, he got the knighthood because of his invention, and you can see it was invented in what, about 70 years ago. This is the first time he made all flat sheet glass, which is transparent and smooth on both sides, are made this way. What he did was something very interesting. As you said, there is a metal, but that metal is a liquid. It's in a molten state. He thought of low melting metals. Tin is one of those. Melts at 232 degrees centigrade. So you have a conveyor belt on which molten tin is flowing, and of course, because it's molten, you get a very, very smooth surface, and the molten glass is introduced over the molten tin. And of course, the glass has a higher melting temperature than the tin. And the tin also has another property that finally, when the tin and the glass are removed, there is no contamination of tin in the glass. Now, this is also important because the tin is molten. You have to make sure that there is no turbulence at the time that this molten glass is introduced, because then there'll be a mix-up, and you might actually get contamination of tin in the glass. So obviously, it has to be almost like introduced in a laminar flow, so that there is no turbulence. And so what now is happening is two are basically going in the conveyor belt with the glass riding piggyback on the molten tin. One of the things is that the glass is also being gradually cooled while it is going past. And now when you're cooling, and because it's a molten glass, there's always a fear of entrapment of bubbles. Anytime you introduce a bubble into the glass, it will be a scattering site. There will be distortions. There will be all kinds of problems. So what they do is that while it is being cooled, there is a method by which they remove all trapped air bubbles. Because the glass is still a liquid, so they are able to remove all the bubbles. Then what they do is gradually, after the bubbles have been removed, it's slowly being annealed while it's solidifying. So the glass is beginning to solidify. When the glass begins to solidify around, let's say around 900 degree to 1000 degrees centigrade, what will happen to the tin?
So it would still be a liquid.
Absolutely, it will be a liquid. So what will happen is that your glass is just moving forward, and your tin will fall into maybe a drum, okay, and from where it will again get recycled in this place in the conveyor belt, okay. And so now you have got your glass separated from your tin, and it's absolutely smooth on both sides. And look at the length of the glass you can make. Something like 600 meters, 0.6 kilometers. That's the kind of length of each of these sheets, and then first you cut it to the right size. This is how we get such beautiful flat glass, and that's one of the biggest applications of soda ash because of this particular reaction. Because the sodium is, as you can see, the green predominantly. It would be sodium, and then of course there will be other things like calcium oxide and other stuff. All clear?
So can you please repeat the properties of tin as to why we use it?
It's used because one is that it's a low melting metal. Second, in fact, there's another point which I did not mention. I'm glad you asked the question.
So it is also a high boiling point, so it wouldn't vaporize.
Yeah, it won't vaporize, of course.
Or otherwise.
Yeah, that's a very good point. So it will melt but not vaporize. Excellent point. Let me write it down. Will not vaporize in the temperature range where glass is molten. And there is another important thing about metal. What is that? Which will be important here is as you're cooling the glass.
Conduct heat.
Absolutely. Has high thermal conductivity. You need to remove the heat. Okay, so the molten tin provides a very good medium for the conduction of the heat, and you're not just dependent on radiative transfer of heat, which will of course take place from the surface of the glass. So these would be the typical properties.
I have just one more doubt, sir.
Yeah.
So how does tin basically ensure the planarity of the glass?
Because tin is there are two things. Tin in a molten state will form a smooth surface, like all liquids. So that's effectively what you're having.
And molten tin is much more dense than molten glass. So the molten glass will basically float over the molten tin.
This is a good point. One will have to make sure that while the conveyor belt is moving, that there is no up and down, which can lead to a corrugation effect. I think that there is very precise engineering, but by virtue of the fact that it is a molten liquid, on the surface it will be leveled out smooth. Okay?
Yes, sir. Thank you, sir.
That's the one of the biggest applications of soda ash. Does this kind of a thing, of tin being molten, while glass is being produced, does it remind you of something else which we have learned by analogy? How was vanadium pentoxide used?
So it was melted liquid.
Molten state.
Yes, sir.
You can see it's interesting. Things which are normally solid and you'll always imagine them as solids, but under the conditions of use, they are molten. And this is what you'll find. Innovation in many of these industries will come from this kind of experience of things which have been done in the past, which will help you to perhaps think in a slightly different way. Okay. Now, let me also, I frequently will digress, like I'm going to do now here. Don't be surprised if there are also significant changes in the kind of feedstock that we require for different things. Like, for example, today we are talking about getting sand, silica, and then you are reacting it with sodium carbonate. Now, what is very interesting is that if you take certain biomass, like for example, take rice straw, it's very interesting that when you burn that rice straw, it's frequently used as a fuel, and you compare with the typical composition of glass, as I've shown you, it looks surprisingly similar. Can you see that? Can you
Yes,
see
sir.
this? The B and the C?
Yes, sir.
Yes, sir.
There's the increasing importance of biomass. You can either look at it only for its calorific value, or you can say, hey, what about all the ash, etc., which is left behind? Is there some utility of those? I mean, of course, it can be put back into the fields, agriculture fields, because it will provide some of the minerals which were taken up from the field by the plant. That's how the ash got into the rice straw. But you can also say, hey, why don't I try to see it's so similar? Why don't I just make glass out of it? And you can see when I was looking around, I found there's a paper in 2009, rice straw ash as a raw material for glass production. When you are looking at potentially absolutely breakthrough ideas, look at things like that. Look at always, what are the byproducts? What are their properties? Those be of some use. Let me ask you, for example, okay, so there are some differences, of course, say between this and this. So what would I do to make it exact?
So add more alkalis.
Yeah, actually, you can add more of these alkalis as required, or if there's too much of it, add more silica. So, I mean, it need not be a perfect composition. You can play this kind of a game. You just top up with whatever is deficient, and that's the way you will reach the right composition. Because after all, these are going to be melted. So there will be a uniformity of mixing, which will happen when these things are molten. So absolutely, I mean, so it's not as if they have to be perfectly exact. So long as the bulk of it is coming from this, I'll just top it up with whatever I require. All clear?
Yes, sir.
Yes, sir.
Of course, very important application of soda ash, as you know, is in detergents. You can imagine how many clothes are washed every day, all over the world. So that's a huge application. Plus, you'll be learning about how soda ash is made. When you wash clothes, it's not just about only soda ash. you also have that bleaching. And earlier days, of course, we saw people use bleaching powder, but today nobody uses bleaching powder in detergent. Most of it will be relatively milder bleaching agents, things like hydrogen peroxide. But then hydrogen peroxide is a liquid, not so easy to actually use in a washing machine or when you're washing clothes. Now look at this amazing property of soda ash. When you react soda ash with hydrogen peroxide, okay, which is a liquid and soda ash is a solid, and suppose you're crystallizing the soda ash in the presence of hydrogen peroxide, what happens is that the hydrogen peroxide gets incorporated in the structure of soda ash. This is your H2O2. You can see two oxygens. Okay? And it forms a beautiful solid, a crystalline solid. So you wouldn't even know that there is a bleaching agent in it, and that's what we call sodium percarbonate. It's just a loose van der Waals type of interaction between the sodium carbonate and hydrogen peroxide, and there's no fundamental change in the nature of the bond of hydrogen peroxide or of sodium carbonate. It gets entrapped. I can use this. I just use sodium percarbonate to get the typical detergency action of sodium carbonate plus the bleaching action of hydrogen peroxide. And just like you saw how molten vanadium pentoxide and molten tin have some kind of a relationship. So similarly here, things that we found, similar stories. Chlorine, how it became bleaching powder, difficult to use, easy to use. Acetylene, difficult to use, put in acetone, form the solution, volatilize it, and you have got your acetylene outside. Or hydrogen peroxide, liquid, forms a beautiful solid with sodium carbonate. You will find in industrial chemistry, there will be certain themes which will run across many technologies. And what you should try and pick out are those common themes. That's what will be very useful to you in the future. Okay, let's now go to sodium carbonate. Okay, now this is again something extremely interesting. I don't think you know this information. In fact, I myself didn't. It was one of my students around 2005 or 6 who sent me this patent because we were working on potassium, and so he sent me this. What is the composition of soda ash? What is it?
Sodium carbonate.
Yeah, means Na2CO3. The carbonate part is the one which is actually giving you the alkalinity. Suppose you take wood and burn wood. The ash from the wood, it contains a fair amount of potassium carbonate. In fact, it's not very clear, but the term potash is actually potassium containing ash in wood. That's really one origin of potash, and the other is of course a pot of ash. But I think probably in the context of potassium, probably it would be potassium containing ash. Now, what is very interesting is that the first US patent that was granted, you can see X00001, 1790, signed by George Washington, is, on what? It's basically on a improved method of making potash, making that ash, and that's what the patent is. And it had a huge impact because till sodium carbonate came into play, the alkali which people use, it's not as if there was no industry. There was industry based on this sort of alkali, but it was all potassium carbonate based, not sodium carbonate based. And they had not found mines of sodium carbonate, which today you have in places like the US or in Kenya, Magadi mines. They are all mines of sodium carbonate. Now, what is very interesting is that what this patent is also about, so that earlier days what people were doing was when they were burning wood, obviously getting energy, and then they were just taking that ash, and then people found that it has got potassium carbonate and it became a very useful material. But somebody always is looking for what are the deficiencies of products rather than all the good things about them. And this person, Samuel Hopkins, who was granted the first patent, he realized that this material was very blackish in color. He concluded that black stuff is really all unburnt carbon, that all the carbon in the wood had not combusted and gone away, you know. And so he carried out a second burning of the ash under better conditions, and where the carbon got completely incinerated and the product became absolutely white. Right? And the second thing was, because that carbon was burning, so obviously it generated a fair amount of carbon dioxide from the combustion of the carbon. And so if there was incomplete conversion of potassium oxides into carbonate, that became more complete. And so you ended up getting a higher yield of potash plus a whiter product. And the third thing that he did, which is very interesting, that after that what he was doing was he was just leaching out the potash with water. And what he did was he actually realized that some amount of stuff is still present in the ash. Maybe it is present somewhere, you know, inside the particles of ash, and it's not so easy to leach out. And so what he did, he took the insoluble and put it back into the next lot of wood. Yeah. And so he kept recycling the stuff like that. And the sum and substance is that it actually helped to make a much better product, and also he reduced the transportation cost. Canada and America, etc., were the places where huge amount of wood was being burned for ash. And then these things were being sent by sea to Europe, which was a place where the glass industry was very big, especially in France. So there were massive gains which occurred, and that's the reason why it was the first patent. Now, there's another reason why I thought I will mention this to you. I think I want to dispel myth about patents. You know, the kind of inventiveness, originality, etc., that you require is not beyond any of you. I think any of you are smart enough to have thought of this. I mean, there's nothing extraordinary about this, either in terms of technology or in a thought process. But even so, only some people think of it and others don't. Bear that in mind. So nothing that I'm telling you is beyond you. You could have been that person also, you know, if you were there at the time. What is very interesting also is that the year that the first patent was granted for potash, you know, which is potassium carbonate, was also the same year in which soda ash was made for the first time, made by the Leblanc process. Amazing, you know, same year. Let us try and see what was the origin of that. Europe was the place with all the technologies. Because Europe, which was really the center of technology. Europe was the center of the Industrial Revolution. And one of the things which was very big was glass making, especially in France. You know? And it was a booming industry. The French realized that, well, if there's no potash, you know, then we can't make glass. You know, we'll need potash. And they said that, look, this natural stuff is very unpredictable. You know, how much will be the availability, and it's also limited. You know? And so the French Academy introduced a competition. They basically told people that can you see if you can develop a technology for making something like alkali. You know? They didn't say sodium carbonate, because you could have also made sodium hydroxide. People knew that you can combine sodium hydroxide with CO2 and it will form sodium carbonate. You know, so they were a little broader. Remember, we are talking about things long before they have been invented. They were just building concepts and ideas in their head. So I'll just read it out to you over here, what they said. In 1775, the French Academy offered a prize of 2,400 livres, whatever was the unit in France, you know, of their currency, for anyone who should find the most simple and economical method to decompose in bulk salts from the sea, extract the alkali which forms their base in its pure state, free from any acid or neutral combination, in such a manner that the value of this mineral alkali shall not exceed the price of the product extracted from the best foreign sodas. Now, can you imagine? Now it might seem a little more obvious because we talked about how you can take sodium sulfate and through bipolar electrodialysis you can make sodium hydroxide and sulfuric acid. Those technologies came much later, but this much people knew that if I've got, let's say, sodium sulfate or sodium chloride, which I can take out from the sea, and the sea is an abundance of salt, after all, what is a salt? We have all learned. A salt is basically only a combination of an acid and an alkali. So effectively, what these people were asking was, can you reverse the process? And reverse it in a way that I only get the alkali part. I don't know what you're going to do with the acid part. We'll find some solution and it'll go. But I just want to be left with the alkali. And second, it has to be not something very costly. It has to be able to compete with maybe some amount of natural soda that had become available at that time from some mines, apart from the potassium carbonate from the plant. But they said you have to compete with that, otherwise we are not interested. And it was this person Leblanc, who took up the challenge. And it's an open challenge. It was given to everybody. And so this person, he said, oh, so this would be interesting to come up with a technology. I hope you can see how to think entirely in a vacuum when nothing exists. Now, the reason why I stress this is that I find that we are not very good at it. Somehow, maybe our education system or whatever, I don't see us as having that level of creativity. We seem to be good at when somebody has done something, we are also good at making it. We are also good at making it cheaper. That kind of thing we are very good at. But those would all fall in the realm of reverse engineering. Something which you are doing for the first time, nobody has done. That I find that we are not so good at, and I would strongly encourage you all to develop that capability. And what that also means is that you have to be fairly thick-skinned, or that you should not feel shy about asking preposterous questions. Be a bit daring and ask questions which have never been asked before. Let's see what Leblanc did, and I will send you this article. It is called the Leblanc soda ash process, a Gothic tale for freshman engineers. I think you'll enjoy reading this article. I'm not very sure whether this was the thought process in Leblanc's mind. I've not seen this articulated so clearly, but what he did was that first, Leblanc, and he just used what Glauber had taught us from the 17th century, that you take any salt, add sulfuric acid to it, and what you'll find is like HCl will come out if it's a chloride salt, or if it's a nitrate salt, then NO2 will come out, which we have learnt in school. So what he did, Leblanc, was that he first took sodium chloride and treated it with sulfuric acid, and effectively, it's something that takes place in two steps, not in one step, because the first step, I think, is exothermic, and the second step is endothermic. So you cannot mix up the two, because then your conversions will be poor. So you have to get the right conditions for the first step and the right conditions for the second step. And it, NaCl gets converted into sodium sulfate. And then what he did was that he actually took that sodium sulfate, which at that time was known as salt cake, sodium sulfate. Okay. He took that sodium sulfate and he added into that limestone, calcium carbonate. Of course, the two don't react on their own. So when things don't react on their own, do the next best thing that you can, heat them up. What do you heat them up with? You heat them up with what is available, coal or wood. So they took coal and put it in, okay, and they heated it up. And probably Leblanc just hoped for the best, What was he possibly hoping for? Let me ask you. He took sodium sulfate and he took calcium carbonate and heated it up. What might he have been hoping to get? I mean, this is speculation. It's not written anywhere, so I'm just imagining. Well, I suppose he knew that calcium also forms a sparingly soluble salt with sulfate, although calcium carbonate is also that. But he probably thought that maybe it will form calcium sulfate, and I'll get my sodium and carbonate to form sodium carbonate. It's like as if I have taken sulfuric acid and I have made a neutralized combination of that, which is calcium sulfate. So I've taken away the sulfate part from the seawater, and I've just been left with the sodium to combine with the carbonate to form sodium carbonate, which would be in the spirit of what probably the French Academy had thought. That's not exactly what he ended up with. He found that the sodium sulfate is reduced by the carbon to sodium sulfide, and it releases carbon monoxide, CO. And later on, the sodium sulfide reacts with calcium carbonate and it forms sodium carbonate, and instead of getting calcium sulfate, which he might have expected, he ended up with calcium sulfide. This step was all known before, known by Glover. The radical innovation was this step. This is something nobody had done before. I can write it down as sodium sulfate plus calcium carbonate plus carbon is giving sodium carbonate plus calcium sulfide plus carbon dioxide. But it was also a big mess because the calcium sulfide and this whole stuff formed a black, terrible looking ash. And there were huge problems with this technology and to extract out sodium carbonate from that, to deal with all the waste, etc. So that was one problem. I'm sure Leblanc, like Alfred Nobel, probably, although they did some great things, but both were probably cursed, for having ruined the lives of many people. And Leblanc also introduced probably the worst pollution through his process, but he developed a great product, Leblanc process, okay, which lasted for what, almost 100 years or thereabouts. And but tragically, what happened was that Leblanc required sulfuric acid to form sodium sulfate, and sulfuric acid was produced in those days by the chamber process. Okay. So what was required to make sulfuric acid then? Well, I needed sulfur to make SO2, right?
Yes, sir.
Yes.
Yeah, and I needed also chili saltpeter because it had to be catalyzed by nitrogen oxides. What happened was that because of wars, all the sulfur and chili saltpeter got diverted to make weapons. Leblanc had his plant, but he had no raw material. He said, how will I run the factory? Second thing was very tragic. The French government said, Leblanc, you, of course, you have done a great thing and you have invented the soda ash process, wonderful, but you will have to allow other people to also manufacture soda ash. So he had to compulsorily license his process. And so he lost his monopoly. Other people probably started making it even more efficiently than what Leblanc did. So those were problems. And then Leblanc fell into debt. Just imagine the person who created this so-called greatest of technologies, Leblanc. He just could not take it anymore, and he committed suicide in 1806. I mean, after this process had been probably operating for about maybe 20 years or so, 20, 30 years. Okay? How tragic. And oh, there was one more thing. As I said, of course, I didn't mention it, and I'm sure Leblanc received a lot of flack for all the pollution that he introduced. So, what would be some of the pollution problems? What do you see above? What were the problems?
So carbon dioxide was produced.
Carbon dioxide or monoxide? Carbon.
Some
Monoxide.
monoxide was produced.
Achha, one second. CO, which is poisonous. Okay. And what did you say the next one?
So the sludge and its maintenance.
Sludge. Sludge and its maintenance. What else?
So HCl gas is also produced.
Yes. HCl. Can you imagine? This stuff is coming out and it was all going into the atmosphere. Okay, the HCl. And right next to it, I've got calcium sulfide. So what will happen when HCl sees calcium sulfide?
Calcium chloride and
And
H2S. H2S.
H2S. Calcium chloride is not so harmful, but it would form H2S. You know how poisonous H2S is. HCl gas, and from reaction with CAS, you may even get H2S.
Excuse me, sir.
Yeah?
So this H2S, sir, if it was found, sir,
Yeah.
could it be used for production of sulfuric acid again?
We'll come to that. But in the earlier days, it was just, the HCl from the atmosphere would probably have been reacting with the calcium sulfide, and the H2S was going, and there was a stink of H2S. You know how badly H2S smells. Okay? Yes, what you're talking about are all the things that subsequently happened after Leblanc committed suicide. So Leblanc did not live to see all the subsequent improvements which were made to the Leblanc process. Is it clear?
Yes, sir.
Now let us see. So what were the important advances? You all are chemical engineers. You must look at it from an engineering perspective. For one thing, you had to mix three constituents and they have to react. Sodium sulfate, calcium carbonate, coke. How do you mix them intimately? Otherwise, most of the intermediates will just escape and you will not get the main reaction taking place. So these people, Elliot and Russell in 1853, so almost what? Almost half a century after Leblanc committed suicide, these people came up with the rotary furnace. So just like we mix cement, So he put all the stuff in, these two people, and they got a very, very intimate mixing, of these things. And second, because it was done mechanically, and so you did not require labor, for this. So it really brought down the labor cost also substantially. That was one. Second, exactly as you have said, that managing the sludge, and this person, James Shank, he developed very nice methods of a series of vats, tanks, to carry out the leaching process, and did it in a way that he did not expose people, to this terrible thing. So it was done in a kind of closed tanks from which things move from one tank to the other. Okay, so people did not get exposed, because otherwise, even if there was some amount of HCl invariably in the atmosphere, it would get in and people would be smelling this HCl. The third very interesting thing was that this person Gossage, right, he realized that at the heart of both the problems, that is HCl escaping and creating acid all over, and the fact that this H2S is being formed, all of this is linked to the fact that I am letting HCl escape. And so what he said is that I will develop a method for scrubbing HCl with water. And that is the first application of scrubbing. Today, you just say, oh, you put a wet scrubber, you do this, do that. He was the one, and his work led to, in England, the first industrial act. It was known as the Alkali Act, and what they said is that 95% of the emitted HCl must be scrubbed, because already Gossage had devised the method, of scrubbing.
So can you please explain what scrubbing is, sir?
Now, so what you do is that as the HCl is coming out, I need to remove it. Okay, and so what I do is from the top I spray water, and the HCl is coming from the bottom, is going up, and I'm spraying water from the top, and so may not be all of the HCl, but a substantial amount of the HCl will now go into dissolved state, and it will form HCl acid solution, not vapor. Okay?
Yes, sir. Thank you, sir.
All right. And that's what scrubbing is. Right. So we'll see on Monday what were other opportunities which were exploited, and also what were some of the problems which they could not solve in the Leblanc process, and why it subsequently gave birth to the Solvay process.